Hello everyone, I am Dr. Naresh Kumar, Assistant Professor from the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to have a discussion on pulse width modulation inverter. So first here, what do you mean by pulse width modulation? So here the method in the power electronics, so common control method. So that is for managing the output voltage of the converter. So particularly in AC to DC to AC inverters is known as a pulse width modulation. So now here in the output voltage of the voltage source inverter is here. The output voltage of the inverter is fixed. So but here the output current, so V0 is fixed. This is omega T and VDC. This voltage is fixed for full bridge. For our bridge, that is VDC by 2. Now here this is a full bridge inverter. VDC input voltage is VDC, and now here what about the current? Current is depending upon the load. Current is different. For R load it is same as a square wave. For L load, that is a triangular. For RL load, so that is the exponential, and RLC load, that is the sine wave. So now here, output voltage is fixed, but here output voltage should be variable. So that is one drawback of normal output this output voltage. So we need to vary that output voltage. So by using pulse width modulation technique, so here V not equals to sigma n equals to 1, 3, 5 infinity and 4 VDC by n pi sine n omega t. So now here Vrms equals to V0 RMS equals to VDC here for in this waveform, and V0 RMS equals to V01 equals to 4 VDC by pi, and V01 RMS equals to 2 root 2 by 4 VDC by pi and root 2. So that means 2 root 2 VDC by pi. So now here we cannot control. This is fixed. So fixed fundamental output voltage and fixed output voltage. We cannot vary. So now here by using pulse width modulation. So now here pulse width modulation here in this case VDC, and this is the width of pulse by pi. So this I will explain. So now here the basic concept behind the pulse width modulation is adjust the output voltage with pulse width to regulate the output average output voltage. So with PWM, a fixed DC voltage source can produce a sine wave form with variable frequency and output voltages. So now here these are the advantages. So here this technique is used in the LEDs from the overheating while preserving their brightness, and this technology responds quickly and accuracy, and high input power factor is provided by pulse width modulation technique, and motors may provide so their full torque even a lower speed thanks to now here PWM technique. So now what about the disadvantage? So here significant switching losses are a result of high pulse width modulation frequency, and radio frequency interference is caused by this pulse width modulation. So these are the advantages. First definition, advantages and disadvantages. So now here, so the classification of inverters, we have already seen voltage source inverter and current source inverter. In that voltage source inverter, single phase and 3 phase. In the single phase, half bridge and full bridge. Here in the 3 phase, 180 degrees conduction mode and 120 degrees conduction. So there is a variable fixed frequency, fixed voltage inverter and variable voltage inverter. So in the fixed voltage inverter, voltage is fixed and frequency is constant, but here voltage and frequency both are in variable. So now here this is a pulse width modulation technique. So now here the pulse width modulation types are, so first one is a single pulse width modulation, multiple pulse width modulation, sinusoidal pulse width modulation. In this again two types, so unipolar and bipolar. Sinusoidal pulse width modulation, unequal pulse width modulation. So each and everything I will explain. So first single pulse width modulation. So now here this is a only one pulse. So this is a pi and this is a 2 pi. This is half cycle. So now here, so this output voltage waveform symmetrical about the y-axis. So this is the output voltage V0 and this is VDC. Here this is 2D. So 2D. So the pulse width is 2D. In the negative half cycle is also 2D. Single pulse width. So here what do you mean by pulse width? So pulse width equals to width of pulse per half cycle. So now here this one here width of pulse 2D, this is half cycle up to pi, 2D is your pulse. And now here what about your output RMS voltage V0 RMS equals to VDC under root 2D by pi. But in the previous case, in the single phase full bridge inverter, so output RMS voltage equals to VDC and V01 equals to 4 VDC by pi. So this is a fixed, we cannot change, but here it is a variable. Pulse width we can vary. Here this is a single pulse width modulation, and now here this is the multiple PWM. So in the half cycle, so the width of pulse, so here pi 2D by 4 means n 2D by n 2D by n 2D by n. Add all this, you will get the complete 2D, and n is the number of pulses in the half cycle. So width of pulse per half cycle. So that is, so here this is multiple pulse width modulation. So now here unequal pulse width modulation means here unequal pulse width modulation. Unequal pulse width modulation means here, so that I will draw first. Here this is one, this one. So now here this one. Here S1, S2 will conduct and S3 and S4 will conduct in the negative half cycle. And now here, so this is a pi by 2 and this is the pi, and now this is the 3 pi by 2 and this is 2 pi, and now here this is alpha and this is the alpha 1. So pi minus alpha and pi plus alpha 1. So now here what will this is the unequal pulse width wins here. So here S1, S2 will conduct from 0 to alpha, and S3 and S4 will conduct from alpha to pi minus alpha, pi by 2 minus alpha to pi by 2 plus alpha. And next here this pi by 2 plus alpha to pi, and S1, S2 will conduct. Same way here S3 and S4 will conduct, and here S1 and S2 will conduct, S3 and S4 will conduct. So this is here where unequal pulse width means in the 0 to alpha here we are getting more pulse, and here from alpha to pi by 2 minus alpha to pi by 2 plus pi alpha, so we are getting less pulse width. So this is unequal pulse width modulation. So now here what about this sinusoidal pulse width modulation? In this again unipolar and bipolar pulse width. So now here I will draw the unipolar and bipolar. So this is, so I increase the pulse. So now here and increase some pulse and again decrease and again decrease. Now here in the negative and here in the negative same, and now he increase some pulse and next increase some pulse. This should be same, and now decrease and sorry. and it should be so. So now here let me change the color over here. So this is the sinusoidal pulse width. So here at pi by 2 this duration we are getting more pulse. So here this is the unipolar pulse width. So now here what about the bipolar pulse width means here we are getting here same figure, the negative also. This one like this here. So here we are getting half cycle. Same way here like this we will get. So here in the numerator, in the positive part also we will get the waveform. So this is the unipolar and this one is the bipolar. I will explain each and everything. So single pulse modulation technique, multiple pulse width modulation technique, sinusoidal pulse width modulation technique. Next, unequal pulse width modulation. First, I will explain multiple pulse width modulation. Then I will explain single pulse modulation. So here, by putting n equals to 1, you will get simply single pulse modulation. So simply it will be clear. So first, I will explain multiple pulse width modulation. So first here, let me change the color over here. So first, so here I will draw the how this multiple pulse width modulation can be obtained. So first I will draw the diagram. So first this is the triangle carrier waveform. So that is the triangular waveform. So now here this one. So this is the V. So now this is the carrier waveform. Next here this is carrier waveform. So now here V C, and now here let me change the color over here. So this is the reference waveform. Omega T, and this is the V naught, and this is the VF. So now here on in the half side this is a pi and this is the 2 pi. So now here number of how we will get the how to obtain the multiple pulse width. So now better take one comparator. So comparator here. So now here this is the triangular waveform and now here this is a square waveform. So now compare this one, you will get. So when VC is greater than VR, so VC is greater than, so this is reference waveform, VR. So S1, S2 switches will conduct in the full bridge inverter. And now here minus VC is greater than minus VR. So now here S3 and S4 switches will conduct. So here in this case positive VDC, and here in this case minus VDC, negative VDC. Let me draw the graph for this one. So now here how the fundamental output voltage will be obtained. So now here, so this one, here this one, these are the, in this way we will get. So these are the waveforms. So first here let me change the color over here. So let me take this one. So in this one, so VC is greater than VR. So here plus VDC, and S1, S2 switches will conduct S1 and S2. And same way here is also S1, S2 switches will conduct VDC, and here is also VC is greater than VR. And in the next second, in the next half cycle, so this is a pi. And next in the minus VC and minus VC, and this is minus VR. So that is minus VC and this is a minus VR. So minus VC is greater than minus VR. So this condition S4 and S which will conduct. So that is minus VDC. So minus VDC, S3 and S4 switches will conduct. Here is also same. And here is also same. So we are getting the multiple pulses in half cycle, in the complete full cycle. So here we are getting 3 pulses. So how to determine the number of pulses in the half cycle? So now here, so the number of pulses here. So now here that number of pulses, suppose n. So that how to get this one? So here we are getting. So this is a complete. Let me change the color over here. Let me take this color. This color. So now here this is the total time period. So for this reference waveform time period, this square waveform time period is t. So now here up to this one, so this is one, this is the t by tr by 2. So now here what about this one? What about this waveform? This is the tc and tc. So this time period is tc. So now 3tc equals to tr by 2. 3tc equals to tr by 2. So now here number of carrier waveforms. Here number of carrier waveforms, here 3. So if n number means that is n. So now here ntc equals to ntr by 2. So n equals to, if you convert in the frequency, so 1 by 2 fr into fc. So this is the number of pulses. So here number of pulses in the half wave. So here that equals to fc by, so frequency, carrier frequency divided by 2 into reference frequency. This formula is most important. So now here my question, how to find out? So this one. So my question, another question is here. Let me take. So this pulse width, how much pulse width? So pulse width, this 2d equals how much pulse width we will get. So now let me take this triangle. So this one. So now here I am drawing the triangle. So here I am drawing the triangle. So this is the VC, and now here this is the VR, and this length is VR minus VC, and this is your pulse width 2D. So that is pulse width, and this you need to determine. So now here what about this one? This one. So this is the pi. So pi by 3. So this is a pi by n. So total pulse width is pi by n. So now this is A, B, C and D and E. So now here let me write here that this one. So here this length is VR VC minus VR. So now here this one C now this one. So A, B, C. So now here this is D, E, F. So now here CF divided by and this one, this length is, what about this length? This height is, so that is VR. VR means that is suppose BC. So that is VR. So now here VC minus VR and this one is VC, sorry. So this one is VC, and now here what about this one? So this pulse width is 2D, means pulse width divided by pi by n. So now here this pulse width we need. So that this is VC minus VR. So now here VC cancel 1 minus VR. So that equals to pi by n. So VC minus VR by VC. So that equals pi by n minus 1 minus VR by VC. So that equals pi by n into 1 minus m. So VR minus VC is the modulation index. So this is your complete pulse width. So this complete pulse width equals to pi by n. So 1 minus m. So this is your m is the modulation index. So now here another thing is, so how to get the multiple modulation technique, and next how possible number of pulses in half cycle. So that is VC FC by FR into 2, and now here the pulse width equals to n by pi n pi this pi minus pi by n into 1 minus n is the number of pulses. And next another pulse is here. Next determination is here. So space width. So now here let me draw the graph first. So now here this is the 3 pulses in the half cycle. So omega t and V naught. So now let me change the color over here. So this is VDC. So now here it is 2D. So now here this is a pi. So now here 2D by n and this pulse width 2D by n and 2D by n. So total pulse width is here 2D only. So now if you divide this number of pulses means to each pulse width is 2D by n, 2D by n, 2D by n. So now here this is your gamma. So now here space width, each space width you will calculate. So now here how to calculate this one, this one and this one, 4 pulse widths. So now here this one equals to gamma minus, so this length equals to, so 4 into 1, 2, 3, 4 space width equals 4 into, now here gamma minus this length. So gamma minus, so this length is d by 2 here, d by 2 here, gamma minus d by n plus total pulse width. So 2d by n plus 2d by n plus 2d by n. So that is 2d only, that equals to pi. This expression is most important. So here 4 equals to, so here we have 3 pulses, we are getting 4 space widths. So n plus 1 into gamma minus d by n plus 2d equals to pi. So now here gamma value is most important. This why I am determining this gamma I will explain in the next. So now here this equals to pi minus 2d by n plus 1 plus d by n. So this is most important formula. So this gamma equals to pi minus 2d by n plus 1, this d by n. And now here one more thing, what is the expression for output voltage? Output voltage equals to, so that equals to V naught equals to sigma n equals to 1, 3, 5 and infinity. And next here 4 VDC by n pi sin n omega t. So this is our actual in the full bridge inverter. So now here gamma, how you will calculate gamma? So here we are getting the half wave symmetry, output voltage, how you will calculate? So here output voltage Fourier series expression we need to derive. So in that case gamma is most important place, more is important term. So that is the reason I derived this gamma pi minus 2d by n plus 1 d by n. So now here this is half wave symmetry, how symmetric waveform. So that is equals to f of theta equals to minus of f of theta plus pi plus theta. So this we will very know. So in this Bn is not equals to 0, A naught equals to 0 and B naught equals to 0. So now here Bn is equals to, what is the formula? Bn equals to 2 by 2 pi integral of, so now here, so gamma minus, so here gamma minus up to this region only I am in, this one is only I am deriving. So now this one equals to gamma minus, so now here let me take red color, gamma minus d by n, gamma minus d by n and gamma plus d by n. So what is the output voltage? VDC. Now here sin n omega t d omega t. So now here if you integrate, here possible number of how many number of pulses here n, and it is also half symmetry, and that is the 2. So now here 2n into 2 by 2 gets cancelled by 1 by pi. So now here gamma minus d by n, gamma plus d by n. So that is the VDC, that is the cos n omega t. So now this is the case. So in the next case, what is the conclusion? So now here, what is the conclusion here? In the conclusion, so now here, let me take the red color. So now here, what is the conclusion? So output voltage, V output equals to V naught equals to what is the formula? So now here N into sigma, N equals to 135 infinity 4 VDC by N pi sine of ND sine of n into d by n sine n omega naught. So t. This is your final expression for output voltage in the Fourier series expression. So now here in this case, so now this is multiple pulse width modulation. Okay, for single pulse width modulation, so for single pulse width modulation n equals to 1, and for 2 pulse width modulation n equals to 2 and n equals to 3. So what is the formula, and what about the gamma equals to formula? Gamma equals to, for n equals to 1 and n equals to 2 and n equals to 3, gamma equals to pi minus 2d by n plus 1 minus d by n. So this is the gamma formula. So now here for n equals to gamma equals to formula n equals to 1 means here pi by 2 and 2d by 2, and this is d by 2. So now here this is only pi by 2 only, n equals to 1. So this is a pi by 2 for this one. And what about the n equals to 2 here? So this is pi by 3, gamma equals to pi by 3 minus 2 means here minus d by 2d by 3 minus d by 2. So now here this, in this case, so what is the value of 6 minus 4 minus 3? So that equals pi by 3 minus d by 6. So now here same way for gamma n equals to 3. So now here n equals to 1, what is the formula? V naught equals to n equals to 1 sigma n equals to 135 infinity. So here gamma equals pi by 2. Here this is a gamma, sorry, this is a gamma. So n equals pi by 2 means for all pi by 1 pi by 2 3 pi by 2, that value is always 1. So sine 4 VDC by n pi sine n d only, this n value equals to 1. So now here n equals to 2, V naught equals to sigma n equals to 135 infinity 4 VDC by n pi. So now here sine of n into this gamma equals to pi by 3 minus d by 6 and sine of n d by 2. So sine of n omega naught t. So these are the equations. So now here this is regarding multiple pulse width modulation and single pulse width modulation. So now here how you will remove the higher order harmonics from the complete waveforms. So now here let us take, so here 2d equals to 72 degrees. So now here 2d equals to 72 degrees means d equals to 36 degrees. So now here d equals to 36 degrees for n equals to 1. So now here what is the V naught equals to, what is the value you will get here? So for fundamental I am getting, so now here sigma n equals to fundamental means that equals to 4 VDC by pi sine of, so n into so that equals n equals to 1 means that is 36, that equals to 0.74 VDC. And now here this is n equals to 1 only. For n equals to 2, here V naught equals to 4 VDC by, so by 2 also you need to multiply. So 8 by pi sine of here pi by 3 minus 36 by 6, so that is this value equals 0.64 VDC. So now here, so what is the conclusion? So V01 is harmonic is maximum is greater than V01 at n equals to 1 and here n equals to 2. By increasing the number of pulses, by increasing the number of pulses, here by increasing the number of pulses, so here lower order harmonics will decreases. So lower order harmonics will be decreased. So lower order harmonics. Next, higher order harmonics automatically increases. How it will happen? So output voltage is constant here. So Vm1 sine of n is n omega 1 t and Vm2 sine of n omega 2 t, and next is Vmn sine of n omega tn. So now here these are the lower order harmonics are decreasing by increasing the number of pulse. So decreasing means, so it is a fixed, and it is fixed means lower order harmonics are decreasing means automatically higher order harmonics will increases. So by using suitable filter we can remove the higher order harmonics. So here in this way multiple pulse width modulation will work. Okay, so now I hope this pulse width modulation concept and single pulse width modulation and multiple pulse width modulation. Thank you very much to you all.
Like, share and subscribe. Hit the bell icon for more updates.